Hello, welcome to my lecture on signals, amplifiers, and operational amplifiers. My name is Brent Berteau, and this lecture will be referencing Microelectronic Circuits 8th edition by Cedrin Smith. In this lecture, we will cover the following topics: signal amplification, circuit models for amplifiers, the ideal op-amp, inverting configuration, non-inverting configuration, and throughout the lecture we'll do several examples. I will provide timestamps to all of these topics in the description. Let's get started. Let's begin by discussing signal amplification. What is it, and why do we need it? So, amplification is needed when a provided signal is weak and it cannot be accurately processed. Maybe I have some weak AC signal going on, and I'm trying to process this. I can use linear amplification to amplify the magnitude of that signal without actually changing it. This ensures that when I go to process this signal, the information is maintained and it is not distorted. This lecture will only focus on linear amplification. Non-linear amplification can get very messy, and that will be a topic for a later video. Here we just have a simple amplifier with an input signal, and it produces an output signal. And if we're given a voltage amplifier with an input and output voltage, so here would be our input voltage, here would be the output voltage, this amplifier is providing our gain A. A represents the amplification, which we'll oftentimes call A. So these are the three essential equations for amplifier gains. We have a voltage gain, a current gain, and a power gain with every amplifier. We can see these equations where, again, A is the gain in the subscript, just determines what kind of gain. So A sub V means the gain of voltage. So, for example, if we have V in and V out of this amplifier, the voltage gain is just V out divided by V in. If we have an input current and an output current, we can calculate the current gain by dividing the output current by the input current. And as you may know, power is just equal to voltage times current. So naturally, the power gain is just the gain in voltage multiplied by the gain in current. Now, if you're not familiar with decibels, there is another unit often used by electrical engineers, and it's called decibel. It's a logarithmic measurement, and it's often used to express gains. So if you calculate any of these gains, you can convert it to decibel by using a logarithm. Now notice, for voltage and current, you do 20 multiplied by log base 10 of that gain, but for power, it's only 10 multiplied by log base 10 of that gain. Let's try out an example. Let's solve example 1. An amplifier has a voltage gain of 100 volt per volt and a current gain of 1000 amp per amp. Express the voltage and current gains in decibels and find the power gain. Okay, so we know that voltage gain is equal to 100 volt per volt. And to convert this to decibel, we take 20 times log base 10 of the absolute value of our voltage gain, 100 volt per volt, and this is equal to 40 decibel. Now we're given our current gain is equal to 1000 amp per amp. To convert this to decibel, we take 20 log base 10 of the absolute value of 1000. And this is equal to 60 decibel. Now to find the power gain, we can just multiply AV times AI. So that is equal to 100 volt per volt times 1000 amp per amp. So we have 1, 2, 3, 4, 5 zeros. So this would be 1 times 10 to the power of 5 watt per watt. And to convert this into decibel, it would be 10 times log base 10 of 1 times 10 to the power of 5. And that is equal to 50 decibels. Let's continue. This is a circuit model for voltage amplifiers. Now, this can be a little jarring to look at when you first are studying this. So let's try to break this down piece by piece. So Vs and Rs represent the signal source and the signal source's internal resistance. You can see it then conducts this current to Vi and Ri. These are the input source and resistance. So if I was trying to draw out an actual amplifier, I would have my Vs here, my source. Then I would have my source resistance. Now, I would have an input resistance. Then, entering the amplifier would be my input resistance. And inside this amplifier is where this AVO times VI occurs. We are amplifying the actual input. Now, at this point, we're going to distinguish two different types of gains. We have the open circuit amplification, and we have the closed circuit amplification. Whenever you're solving a problem, it should distinguish which one you want to solve for. But essentially, we get a closed circuit amplification once we connect this to a resistor, a load resistance, or any kind of load for that matter. So this is our load resistor. Then the output voltage would be the voltage across the resistor, the load resistor. So I just redrew this circuit as one with an actual amplifier. These will be three equations you're going to use very frequently, so I would take note of these. And let's try to solve some problems using this schematic. Let's solve example 2. A sensor producing a voltage of 1 volt RMS with a source resistance of 1 mega ohm is available to drive a 10 ohm load. If connected directly, what voltage and power level results at the load? Okay, let's focus on this first part. We'll solve the rest of the question after this. First, we need to draw what this is actually describing. So we have a sensor, and it's producing 1 volt RMS, that just means root mean square value, essentially the average value. And it has a source resistance of 1 mega ohm, and it's available to drive a 10 ohm load, and we're connecting it directly, which means there's no amplification yet. So we have our load resistor, which is 10 ohms. So if you were to refer to the last slide with that previous amplifier schematic, this is cutting out the amplifier because it is connected directly. Now we want to figure out what voltage and power levels result at the load. So we can calculate voltage by just using resistor division. So that would be 1 volt times the value of the load resistance divided by the series combination of the source resistance and the load resistance. So that would be 1 volt multiplied by 10 ohms divided by 1 mega ohm plus 10 ohms. So I calculate V out to be 10 microvolts, or 10 times 10 to the negative 6 volts. Now, if we want to calculate the power level, we know that's equal to voltage times current. We also know that current can be expressed as voltage divided by resistance. So we can rewrite the power equation as V squared over R, which for this case would be the output voltage squared divided by the load resistance. So this is equal to 10 times 10 to the negative 6 volts squared divided by 10 ohms. So I get the power level to be 10 to the negative 11 watts. So very low power, very low output voltage. Let's continue solving the rest of the problem and see how the answers change once we add an amplifier. Okay, let's continue solving. So if a unity gain, as in AVO equals 1 buffer amplifier with 1 mega ohm input resistance and 10 ohm output resistance is interposed between source and load, what do the output voltage and power levels become? So this is turning into the original schematic we showed. So let's start drawing it. Again, we have our voltage source of 1 volt, followed by our source resistance of 1 mega ohms. And this time we have a buffer amplifier interposed between source and load, which means next up will be our input resistance, which is stated to be 1 mega ohm. That also means we're going to be reading a input voltage. Okay, so now I want to ground to the left side, isolate it. And now we're going to draw our amplifier, which is equal to AVO times input voltage. It has a 10 ohm output resistance. Then we have our load, which is also 10 ohms still. And this is where we are reading V out. So we have a load, and this is 10 ohms. Okay, we've drawn our circuit. Now let's figure out the output voltage. Well, in order to figure out the output voltage, I need to figure out the voltage supplied by this amplifier. I had already stated that AVO is equal to 1, so I just need to know what my input voltage is, which is over here. So you can see that the input voltage will be equal to the voltage source times the input resistance divided by the series combination of the input resistance and the source resistance. So it's equal to 1 volt times 1 mega ohm divided by 1 mega ohm plus 1 mega ohm. You can see that this is just 1 volt divided by, or 1 volt times 1/2. So that's 0.5 volts. So that means that this amplifier is providing 1 times 0.5 volts. So we're getting 0.5 volts here, which means the output voltage will be 0.5 volts times the resistor division between the load and the output. So this becomes 0.5 volts times 10 ohms divided by 10 ohms plus 10 ohms. Again, this is just 0.5 times 1/2, so we get 0.25 volts for our output. If we want to do a gain in decibels, it would be 20 log base 10 of our voltage gain our voltage gain is equal to V out divided by Vs. This can get confusing. It's not going to be Vi for this amplifier circuit. It's going to be Vs. So that'll be 0.25 divided by 1, which is equal to 0.25. So it will be 20 log base 10 of 0.25 volt to volt. And this is equal to negative 14 decibels. Okay, let's go to the power. So our gain in power becomes the power at the load divided by the power at the input, where the power at the input is going to be the input voltage times the input current. I don't know my input current yet, but I can calculate that pretty fast. It's just V over R, right? So 1 volt divided by the series combination of resistors, so 1 mega ohm plus 1 mega ohm, that is equal to 0.5 microamps. So therefore, input power is equal to my input voltage times my input current, which is 0.25 microamps, because we have 0.5 times 0.5. So my power gain will be the power at the load, which is, again, just V out times I out. So V out, I out divided by VI, I input. You can calculate the input current again the same way, or the output current. That is just 0.5 divided by 10 plus 10. And that's just equal to, let's see, it would be 0.5 divided by 20. And I'll let you simplify that on your own. But we're going to get 25 times 10 to the power of 3 watt per watt, which in decibel would be 10 log times the absolute value. And that is equal to 44 decibels. So a pretty heavy problem, but hopefully you can start to visualize the process of solving these kind of problems. Let's solve example 3. The output voltage of a voltage amplifier has been found to decrease by 20% when a load resistance of 1 kilo ohm is connected. What is the value of the amplifier output resistance, or RO? Okay, so we know that the output voltage given an open circuit is equal to the open circuit amplification multiplied by the input voltage. Now when you add a load or make it a closed circuit, the output voltage is equal to AVO times VI times RL divided by RL plus RO, essentially adding in that extra load factor. So let's just let AVO times VI equal 1, which means that the open circuit voltage will be 1. That means that this closed circuit needs to decrease by 20%, or in other words, it needs to be 0.8. So you have 0.8 is equal to AVO times VI times RL divided by RL plus RO. Now we already stated that AVO times VI is equal to 1. So we get 0.8 is equal to the load resistance of 1 kilo ohm divided by 1 kilo ohm plus the output resistance, which is what we're going to solve for. So let's multiply both sides of the equation by the denominator. So we get 0.8 times 1 kiloohm plus RO is equal to 1 kiloohm, and we can distribute this 0.8 to get 0.8 kiloohms plus 0.8 times RO is equal to 1 kiloohm. We can subtract the 0.8 kiloohms to the other side. So 0.8 kiloohms is equal to 0.2 kiloohms, or excuse me, 0.8 times RO. So therefore RO is equal to 0.2 kiloohms divided by 0.8, which is 250 ohms. And that is our answer. Let's keep going. This slide is outside of the scope of this lecture, but I wanted to provide it to you for future reference. Everything we've been doing so far has been based on the voltage amplifier, but there are 4 types of amplifiers you can use to represent just about any circuit. So naturally we have a current amplifier, which essentially behaves just like the voltage amplifier, but you're swapping voltage sources for current sources. Then we have this transconductance and transresistance amplifier. So I'm not going to go into detail with these 3, but I just wanted you to know that they exist. Let's move on to the ideal operational amplifier. This is the ideal operational amplifier, and it has 5 key characteristics that you're going to see me continually explaining to you throughout the rest of this lecture. Let's walk through all of them one by one real quick. We have infinite input impedance. So you see that terminals 1 and 2 are the input terminals. They have infinite input impedance, which means that they have infinite resistance. Whereas terminal 3 has 0 output impedance, 0 resistance. The third property is that an ideal op-amp has 0 common mode gain. My professor would call this a virtual short. What this means is, if I drew a wire or a short between terminals 1 and 2, I should have a voltage difference of 0 volts, which means the voltage at the positive terminal 2 should be the same as the voltage at the negative terminal 1. Now we also have infinite open loop gain and infinite bandwidth. This will probably be the least important for this lecture, but it just means that in the frequency domain, this operational amplifier produces the same signal no matter what frequency we're operating at. Let's get into some more equations. Oftentimes you'll need to calculate the differential in common mode signals. So if the positive terminal provides an input voltage V2 and the negative terminal provides an input voltage V1, the differential signal is simply just the difference between those 2 voltages. The common mode signal would be like having a wire go into the middle of the op-amp and getting rid of these other 2 inputs. It's simply just the average of V1 and V2. And you likewise can solve for V1 and V2 using these values. Okay, let's discuss the inverting op-amp, and we're going to show how these 5 key characteristics apply to it. The purpose of an inverting op-amp is to take an input signal, amplify it, and invert or negate the output. I'll return to these closed loop gain things in a second, but first I want to just focus on the key characteristics. So there's infinite input impedance. So here at this negative and positive terminal, we have infinite input impedance. We have 0 output impedance. We should have a voltage difference of 0 across terminals 1 and 2. We have infinite open loop gain and infinite bandwidth. So if I have an input signal, I can determine the gain given its output signal by just dividing the output voltage divided by the input voltage. And for an inverting op-amp, this is equivalent to resistor 2 divided by resistor 1 negated. Now this will be important for later, You see, for the ideal op-amp, we consider infinite open loop gain, but if we're not ideal, we're working in the real world, and there's a finite open loop gain, this is how you would calculate G more accurately. So let's try an example with an inverting op-amp. Let's solve example 4. Assuming an ideal op-amp, find all these values, and also determine the voltage gain, current gain, and power gain. This can look overwhelming at first, but you're going to see how we can use these characteristics of an ideal op-amp to really make this problem a lot simpler. So first off, we can identify that there is zero input impedance at the negative and positive terminals. And we know that V is equal to IR. But if the resistance here is infinite, that means I is equal to V divided by infinity. So that means there's zero current coming into here, and zero current coming into this positive terminal. Now we know based on KCL that the current entering the loop, or entering a node, needs to be equal to the current exiting a node. So take a look at this node here. I1 is entering the node, and there's only one current exiting the node, I2, because there's zero current on this wire. So I already know that I1 is equal to I2. So if I can solve for I1, I'm going to have a lot easier time with the rest of the problem. What's V1? Well, let's leverage this property, virtual short. The voltage difference between the negative and positive terminal should be 0 volts. And because the positive terminal is grounded at 0 volts, we know that it has to be 0 volts at the negative terminal. And therefore V1 is equal to 0 volts. So now I can solve for I1 and I2. It will be equal to 2 volts minus 0 volts divided by 1 kilo ohm, which is equal to 2 milliamps. Excellent. Let's continue with V out. So I can say that V out using Kirchhoff's voltage law is equal to V1 minus the voltage drop across this 5 kilo ohm resistor, I2 times R2. So that's equal to 0 volts minus 2 milliamps times 5 kilo ohms, which is equal to negative 10 volts. Okay, now we just need load current and the output current. So load current, if I know that my voltage here is negative 10 volts, then I can say that the load current is equal to negative 10 volts divided by 1 kilo ohm. That is equal to negative 10 milliamps. And again, the current entering a node should be equal to the current exiting a node. So that means IO plus I2 is equal to IL, because output current and I2 enter the node, load current exits the node. So I have output current equals load current minus I2. So that's equal to negative 10 milliamps minus 2 milliamps. So my output current is negative 12 milliamps. Okay, those are all the voltages, or excuse me, values that we need to figure out. Now we just need to determine voltage, current, and power gain. So voltage gain is VO divided by VN, where VN would be this 2 volts. So we're going to get negative 10 volts divided by 2 volts is equal to negative 5 volt per volt. In decibel, this is 14. Current gain will be output current divided by input current, which in this case would just be I1. So that's going to be negative 12 milliamps divided by 2 milliamps. That's equal to, let's see, excuse me. This should be actually the load current, not the output current. It can be very confusing, as I just made that mistake. Whenever you're calculating gain, you always want to focus on the load, not this output current over here. So we actually get negative 5 amp per amp. In dB, this is equal to 14 decibels again. Lastly, power gain will just be output voltage times load current. So that is negative 10 volts times load current, negative 10 milliamps, divided by input voltage, 2 volts, times input current, 2 milliamps. So the power gain is equal to 25 watt per watt, and in decibel, this is equal to 14. I wanted to show the decibel calculations because for an ideal op-amp, you should expect all of the gains to be the same in decibel, 14, 14, 14. That's another way to make sure that all of your calculations are correct. Now this is the non-inverting configuration of an op-amp. So given a closed loop gain G, we can calculate the amplification to be V out divided by V in again, which for the non-inverting configuration is 1 plus R2 divided by R1. So we see that the input voltage is now connected to the positive terminal. The resistor is still connected to the negative terminal, and now it's grounded. Now, if we don't have infinite open loop gain, we can calculate G more accurately using this equation. So let's try another example, but this time with the non-inverting configuration. Okay, let's solve example 5. We have a very similar setup to the last example, but now we're just using the inverting configuration. So we want to first find IL. But recall, we have infinite input impedance for an ideal op-amp. R equals infinity, which means I is equal to Vn, 1 volt, divided by infinity, which is 0. Therefore, IL is equal to 0. Now we can use the virtual short property to figure out V1. We know that this should have a voltage difference of 0 volts. Therefore, V1 should just be equal to Vn, which is 1 volt. So far, so good. Again, we have infinite input impedance, which means there is no current in this terminal, which means I1 has to be equal to I2, which we can calculate as 1 volt divided by 1 kilo ohm, right? Just V1 divided by that 1 kilo ohm. That is 1 milliamp. Now we can calculate V out. If we're going kind of following the circuit this way, we would have V out is equal to V1 plus I2 times those 9 kilo ohms. So that's equal to 1 volt plus 1 milliamp times 9 kilo ohms. So I get V out is equal to 10 volts. So underline these, and then we can find the low current now because we have 10 volts at this node. So IL is equal to 10 volts divided by 1 kilo ohm, which is another 10 milliamps. Okay. We know that IO is the only one entering this node, and we have IL and I2 exiting the node. So IO should be equal to I2 plus IL, which is equal to 1 milliamp, plus 10 milliamps, which is equal to 11 milliamps. And those are all the values we wanted to solve for. Now let's solve for our gains. So our voltage gain is equal to output voltage divided by input voltage, which is, let's see, 10 volts divided by 1 volt. So that is 10 volt per volt, which is equal to 20 decibels. Now our current gain is going to be kind of interesting. So it should be equal to the load current divided by the input current. But for non-inverting in configurations, we have 0 input current, and our load current was 10 milliamps. So this is equal to infinity. That also means because our power gain is our load power divided by input power, which is V out times IL divided by Vn times In. Well, again, this is This is 0. So we're going to get infinity again. So for non-inverting configurations, if it's an ideal op-amp, you can expect infinite current and power gain. It's pretty interesting. For more practice problems, you can refer to my microelectronic circuits playlist on YouTube, where I walk through multiple different problems from the textbook. If you go to the playlist, it will be chapters 1 and 2 that this lecture covers. And note that this lecture only covered really basic configurations of op-amps, but there are many more configurations to be studied. They're very advanced topics, and I may make a video on them soon. And that concludes my lecture. Thank you very much for watching. If you have any questions, queries, or comments, you can feel free to contact me at my email provided. Have a nice day.